Hello, my name is Michael Clayman, and I am the internal sales engineer for PR Electronics in the USA office. Today, we will be taking a look at how frequency signals are measured. We will send out a link to this recording later for your reference. Before we start talking about what a frequency signal looks like, let's talk about where we might find this type of signal in an industrial environment. A frequency sensor is typically used to measure the speed of something. Maybe there is a mixer that rotates at a certain speed. A frequency sensor can measure the revolutions per minute, or RPM, to indicate the speed of rotation to an operator. There might be a conveyor belt that feeds material to a process that needs to stay within a certain range of speeds to avoid problems. And the speed can be measured in a unit, like how many meters per second something moves along the conveyor belt. Liquids and gases moving through a pipe travel at a certain speed. If we know the diameter of the pipe and the speed of flow, we can determine the flow rate, perhaps how many gallons per minute are flowing through the pipe. Now we can calculate how long it will take to fill a container with water, or how much gasoline is being delivered to a customer. Now that we've seen why it's important to be able to measure frequency signals, let's now take a look at how a frequency signal is generated and how that signal can be measured. Let's take a look at the sine wave in the middle, which has 3 peaks and 3 valleys. We can say that this is a graph of a voltage signal that changes from 0 volts up to positive 10 volts, all the way down to negative 10 volts, and back up to 0 volts. This signal is now back to where it started. This change in signal value is called 1 cycle. And let's say that it takes 1 second for the signal to complete 1 cycle. If the signal repeats at the same rate of once per second continuously, you can say that the signal is changing at a frequency of 1 cycle per second. Another way to say this is that if you pick a point in this cycle, the positive 10 volt peak, for example, as the signal changes in voltage level, you will see that peak again happen in the next cycle in 1 second. That plus 10 volt peak happens at a frequency of once per second. You can see that there is an inverse relationship between the period of 1 cycle and the signal frequency, and that there are 2 simple formulas that describe this relationship. The period of 1 cycle in seconds equals 1 divided by the frequency. Frequency equals 1 divided by the period of 1 cycle. So, if you know the frequency of a signal, you can easily determine the period of 1 cycle. And if you know the period of 1 cycle, you can determine the frequency of the signal. Now, another name for cycle per second is hertz. So this signal is changing at a frequency of 1 hertz. At the top is an example of a higher frequency signal. Each cycle has a period of only 1/10 of a second. So this signal changes at a frequency of 10 cycles per second, or 10 hertz. The bottom sine wave is changing slower, and it shows just 1 complete cycle. Each cycle has a period of 3 seconds, so the frequency of this signal is 1/3 of a cycle per second, or 0.3 hertz. When it comes to measuring a frequency, the amplitude of the signal and the peak positive or negative voltage levels of the signal do not determine the signal's frequency. Only the period of each cycle determines the frequency. Frequency signals can have different shapes. The sinusoidal shape shown on the last slide is commonly created by AC power and tacho generators. However, most frequency signals have a different shape. It usually does not matter what shape the frequency signal has, as long as the signal changes in a repeating pattern so that the period of each cycle can be measured. An important characteristic of frequency signals is called duty cycle. This describes the amount of time the signal is on versus the amount of time the signal is off. All of these signals have the same period for 1 cycle, so they have the same frequency. The top signal is called a square wave because it changes abruptly from being on to being off and spends an equal amount of time in each state. It doesn't gradually change in signal level like a sine wave does. It is on 50% of the time and off 50% of the time. So you can say that this frequency has a 50% duty cycle. The middle signal is a pulse that is on 25% of the time. So you can say it has a 25% duty cycle. The bottom signal is on 75% of the time. So you can say that it has a 75% duty cycle. Even though each of these signals has a different duty cycle, the leading edge of each peak starts at the same time in all three signals. So they all have the same frequency. The on-off alternating signal is detected by the frequency converter. If we define the on state as a signal level above a specific level, that level is defined as the high trigger level, since the signal triggers the on state as it exceeds that level. We can define a trigger low level the same way, the level which the signal has to come down past in order to register as an off state. For example, a gas turbine has a significantly higher RPM compared to a traditional automobile engine. Since we must place a sensor in a position to measure a speed, things like ambient temperature and mounting positions for the sensor are things to consider as well. A sensor can be mounted in various positions to measure a rotation speed. In the blue sketch at the top, the sensor is positioned in the same plane as a gear, sensing the tops of the gear teeth. But it could also be placed at a right angle to the gear teeth and sense the sides of each tooth. In the bottom blue sketch, the pickup sensor runs off the motor main shaft of a mixer, typically a single cam on the shaft that the sensor is pointed towards. The cam has a gear on it with 25 teeth, so each rotation makes 25 teeth pass by the sensor for every one rotation of the shaft. We can say that this cam has a ratio of 1 to 25. For every one shaft rotation, the sensor sees 25 targets. Thus, we are measuring 25 times more signals than the amount of times the mixer revolves. If the mixer is rotating at 60 RPM, that's the same as 1 revolution per second. The sensor will see 25 rotations per second times 60 seconds in 1 minute, or 1,500 rotations per minute. We will scale that in the downstream frequency converter so that a PLC or display can see that speed. For linear speed, we commonly pick up the pulses from some rotating parts that are directly linked to the linear speed. For example, with the conveyor shown above, the rollers pulling the conveyor belt rotate at a certain speed, which a sensor can measure, which can be converted into the linear speed of the conveyor. Again, the sensor is in a position to measure the gear teeth as targets. Here we have a dedicated ring gear with teeth detected by the sensor. Also very common, this gear is located in the drive assembly with timing belt and pulley. The gearbox has 24 teeth on it, and each tooth is seen as a target by the sensor. So each time the gear spins around once, the sensor has seen 24 teeth pass by it. We can say that this gear has a ratio of 1 to 24. The output from this sensor will be a sine wave with 24 voltage peaks for each rotation of the gear. If we know how far the conveyor travels for each rotation, and now we can measure how long it takes for each rotation to occur, we can easily calculate the speed of the conveyor. Now we can make decisions about if we need to increase or decrease the speed and use that information to control the motor driving the conveyor. There are several ways to measure the flow rate of a liquid or gas through a pipe. A common one is to insert a small turbine with blades into the pipe so that as the liquid flows, it spins a turbine and a sensor sees the blades spin at a certain rate. The faster the flow, the faster the blades spin. It's not always desirable or practical to insert a physical object into the pipe, so ultrasound can also be used. The frequency of the ultrasound pulses changes as the flow rate increases, so the change in flow rate can be measured by listening to the change in ultrasound signal frequency. We have various sensor types to generate the signals we need. The main groups are active and passive sensors. Passive sensors rely on an electric coil and alternating magnetic field producing AC current flowing through the coil. The upper motor-like assembly is a tachometer or generator, producing a sine wave representing the rotational speed. The tachometer is also very often integrated into alternators, pumps, and electrical motors for easy mechanical design. This type of sensor is often called a magnetic pickup. Below, on the left side, is an image showing a few types of inductive pickup sensors, typically with a permanent magnet built in. They will detect a change in the magnetic field when the iron mass passes in front of them and generates a corresponding signal. The passive sensors are often used where powered electronic sensors are not able to be used. For example, high frequency applications and extreme temperatures. A significant disadvantage of the passive sensors is the signal amplitude varies with the speed, so it can be a challenge to set the trigger levels correctly. On the positive side, the sensors are often capable of detecting 30 to 50,000 hertz frequencies and capable of withstanding high temperatures. The active sensors include onboard electronics doing signal conditioning. An advantage, you get a uniform signal, stable amplitude, and thus it is easier to establish reliable trigger levels. Typical active sensors are NAMR, two-wire sensors, or NPN, PNP transistor output sensors, where we have 3 wires for the sensor. Compared to passive inductive sensors, the active sensors typically has a lower upper frequency limit of 5 kilohertz. If an environment has hazardous gases or dusts, that may prohibit active sensors from being installed in those areas to prevent the possibility of an explosion occurring. In these areas, a non-powered passive sensor may be the only option for measuring speed. The signal conditioning built into an active sensor creates a much cleaner signal. The signal shown on the left is from an NPN sensor, and to the right is a signal from a passive inductive sensor. The active signal is uniform and clean. No significant noise to disturb our trigger levels. The passive sensor is obviously not a perfect sine wave signal. The cogs of a gear or wheel are often square or have a hard edge, resulting in an effect on the signal called ripple. The cog of the wheel produces a peak up, detecting iron and the ripple while at the cog, and the peak down, leaving the cog and going back to sensing free air. Sensors can have a wide range of typical signal levels. The active sensor on the left produces a high peak to low peak voltage of 5 volts. The passive sensor on the right produces 200 millivolt peak-to-peak signal up and an 800 millivolt peak-to-peak signal. With low-level signals, it is important to do what is necessary to avoid noise as much as possible. The best practice here is to use shielded cable and pay attention to the routing of the cables. Don't run them too close to cables with high current or cables that are emitting noise, or close to common sources of noise like variable frequency drives for motors. It's a good idea to select the active sensor if you have the option so that you can avoid the passive sensor. That will save you a lot of trouble. If you are experiencing issues with unstable triggers and thus unstable readings, an oscilloscope is useful to establish the baseline of the signal and to determine reliable signal levels. Using NAMR, PNP, and NPN active sensors often makes it easy to match up signal and predefined trigger levels. These types of sensors have predictable, standardized output signals that can make installation and measurement simpler than trying to characterize the output of a passive sensor for each new application. Here we have an NPN sensor with a PR Electronics 4225 frequency converter and its specifications. Let's have a look. When an NPN sensor detects a target, the transistor conducts and the collector-emitter junction resistance drops to just a few ohms. In the example here, the collector and emitter are wired to terminals 43 and 41. When the NPN conducts, the voltage at terminal 43 drops to nearly 0 volts because terminal 41 is at input circuit ground. When the NPN transistor stops conducting, when no target is sensed, the collector-emitter resistance increases to millions of ohms. Terminal 41 and 43 are no longer connected, so the resistor pulls up the voltage at terminal 43 to nearly sensor supply voltage. The 4225 detects a repeating change in voltage with respect to trigger level at terminal 43 as a valid frequency input. The trigger levels for the PR4225 is, for an NPN sensor, fixed at 4 volts and 7 volts, which is suitable for NPN sensors powered by a minimum of 8 volts DC. Most discrete NPN sensors have a third wire. That is used to energize components inside the sensor. The sensor supply at terminal 44 can be used to power the internal components of the sensor. But usually, the sensor is powered locally, and most instruments that have an NPN output are powered by a separate voltage source. So the sensor supply at terminal 44 is only used to provide the pull-up voltage to the resistor. Selecting special voltage input, a feature in the 4225 not seen on many other types of signal conditioners, lets you customize the low voltage and high voltage trigger levels. For example, this signal has an amplitude of 0 to 600 millivolts. The on voltage of 600 millivolts is lower than the high trigger levels established for PNP or TTL inputs, so selecting those input types will not work. The signal simply doesn't reach the trigger level for these input types, so the frequency would not be measured. Also, the off voltage does not go negative, so selecting a tacho input won't work. So instead of using a standardized input type, we need to be able to define the trigger levels for the application so that the frequency can be measured. The 4225 has the ability to customize the input trigger levels, so it can measure the frequency if you define the low trigger level of, for example, 0.25 volts and a high trigger level of 0.5 volts. When the signal changes from 0 to 600 millivolts and back during each cycle, it will pass these trigger level points and the frequency will be measured. Custom trigger levels are also useful if electromagnetic interference is affecting the signal. Here, the frequency input is corrupted by a high level of electrical noise. To measure the frequency, select high and low trigger levels that are above or below the noise level. In this example, increasing the low trigger level to 0.45 volts allows correct frequency measurement while ignoring the noise. The difference between the low and high trigger levels must be a span of at least 50 millivolts. Sometimes, the device creating a frequency output produces a stable low voltage level, but does not drive the frequency signal up to a stable high voltage level. The floating on-state voltage might not be high enough to trigger the high trigger point, producing erratic results. Also, the floating voltage can be easily affected by electrical noise. If this is the case, selecting pull-up connects the internal pull-up resistor between the sensor supply and terminal 43, ensuring that the on state of the voltage is at a stable high voltage level. Inversely, sometimes the device creating a frequency output drives the frequency up to a high voltage level, but does not drive the frequency down to a low voltage. The floating off-state voltage might be higher than the low trigger point, and the floating off-state voltage is easily affected by electrical noise. In this case, selecting pull down connects the internal pull down resistor between input circuit ground to terminal 43, ensuring that the off state is at a stable low voltage. In most cases where a special voltage input is required, the device creating the frequency output already has internal circuitry that pulls the frequency up to a high voltage and down to a low voltage. So we do not have to provide pull up or pull down resistors. In that case, selecting high Z, Z stands for impedance. When high Z is selected, pull up and pull down resistors are not used, and the input impedance between terminals 41 and 43 increases to at least 100,000 ohms. Measuring an analog signal like current and voltage is not time dependent. The signal might change from second to second, but it's always there at the moment you look for it. Measuring frequency introduces some unique measurement challenges to getting the desired result we are aiming for. Let's consider this situation. Let's say we have a flow meter that measures flow coming from a dispensing pump. We can see on a display that we are dispensing 1 liter per minute of liquid into our process. Our flow meter creates a pulse for every 1/60th of a liter, so a pulse every second. The dispenser pump is then shut off to stop the flow, but the display still shows a 0.2 liter per minute flow rate after a few seconds. Why? The graph here might help us explain the situation. The dispenser pump generates a signal with a period of 1 second, which equals 1 hertz. Here we have a trigger on the high level, the red arrows, which determines the start of the period. No later than 1 second later, we expect a transition from low trigger level to the next high trigger level to happen to establish a confirmation of our 1 hertz signal being measured. If that next pulse does not occur, the orange arrow, the frequency measurement establishes a longer period, 1 over t, since the last pulse. The process value on the display is subsequently updated while waiting for the next pulse. 1 over 1 second is a 1 hertz frequency, but after 3 seconds of waiting, 1 over 3 seconds is a 0.3 hertz frequency. After 10 seconds of waiting, 1 over 10 seconds is a 0.1 hertz frequency, which is still not zero. So when the flow rate goes to zero, the display still shows a small flow rate. With certain frequency converters, like the PR4225, we can introduce the concept of setting the process value to zero after a predefined period of no pulses being seen. Here it is default activated after 1,111 seconds, or it can be set to a 2-second timeout as an alternative. This is very helpful to the operator. When the pump is stopped and there's no flow rate, the display goes to zero, confirming that there's no flow. Now, let's take a look at the PR electronics devices that work with frequency signals. PR electronics has a wide range of frequency converters, covering different needs. Our legacy products, 2255, 5223, 5225 DIN rail converters, and 5725 frequency display come in handy for many applications. PR Electronics has recently introduced the 3225 and 4225, making it much easier to program, install, and implement frequency converters into an even wider range of applications. The new 3225 and 4225 support higher input frequencies than our legacy devices, up to 100,000 hertz. The 3225 is very useful if you're looking for compact and versatile frequency conversion to analog signals, supporting voltage and current, or if you need a trip amplifier or speed guard with a relay output. The 4225 is a member of our multifunctional transmitter family, the PR4000 series, which we will focus on in the next few slides. Our older 5223 and 5225 are frequency converters with PC programmable features. The most prominent feature to the 5000 series devices is the ability to divide pulses over time, perfect for metering applications. The 5725 combines a display and frequency converters into one panel mount unit. Performance made smarter is our slogan. That is also the foundation for the PR4225. High performance with universal power supply, low power dissipation, fast response time, and galvanic isolation on all ports makes it the perfect solution when converting frequency to analog, NPN, or relay output. These outputs can be specified by ordering one of the 3 versions of the 4225, either A, B, or C, whichever one fits the application. By combining it with one of our 4511 displays, you can add Modbus RTU output. Using a 4512 display, instead, enables Bluetooth programming and data logging. All typical sensors and signals are supported, including NAMR, NPN, PNP, TTL, TACO, contact, or custom trigger levels that you can program to match your signal. The 3 product variants of 4225A, B, and C support combinations of analog, frequency, and relay output. Various analog ranges can be applied. Even inverse or bipolar signals can be selected. The current output is typically an active output, but if the PLC is programmed to power the loop, the 2 power sources can fight each other and interfere with the signal measurement. The 4225 can be programmed to produce a passive output in just a few button pushes, which is easier than reprogramming the PLC. All of the PR4000 series devices, including the 4225, include support for universal power supplies and have a high level of galvanic isolation. The converters can be energized with 24 volts plus minus 30%, or typical mains voltage up to 253 volts AC. Polarity doesn't matter. They can be wired in forward or reverse polarity, and they will work just fine. The output relay supports set point, window function, startup delay, on-off delay, and latch functions. Handy features for various applications. As with all PR products, they are engineered with the user in mind. Polarity protected terminals, universal power supplies, low power consumption, eliminating the need for air vents and space between units, make it easy to install and power the devices. An excellent signal-to-noise ratio and first-rate EMC noise immunity allow the signals to come through clearly and continuously with minimal impact from the harsh conditions of the environment. The 3225 and 4225 can also take advantage of the 4500 series of displays, which makes displaying the process and programming simple and easy. The PR4500 series is the market's most intuitive display for programming, monitoring, and diagnostics. These communications interfaces provide intuitive display programming of the PR3225 and 4225 frequency converters. The 4510 display is perfect for simple display and programming. Using the 4511 and 4512 communications enabler, the 4225 frequency converter becomes a Modbus interfaced transmitter, or a Bluetooth-enabled smartphone app programmable transmitter with onboard data logger. Now you don't even have to open the panel door to monitor and program the 4000 series. The communications interface can be snapped onto or off of the 4000 series devices with no effect on their performance. Live monitoring of process value and converter status, backed by the intuitive PR menu design with scrolling help text, makes it really easy to set up the frequency converter. In case you have issues with sensor connectivity, the advanced diagnostic features indicates the possible source of the issue to the user with clear and understandable messages. For advanced use, you can do 2-point calibration, simulation for test or commissioning, and even a copy-paste feature for programming multiple devices. This concludes today's presentation on frequency signals. As I mentioned, a recording of this presentation will be made available soon. Does anyone have any questions?
Thank you very much, Michael. I can see that we have a question and a comment from Christopher Kane. The first comment goes on powering the sensor if it introduces an higher degree of EMC problems if you power the sensor, the active sensor locally. That is how I read the question or the comment. And to be frankly, yes, that could introduce a ground problem, a grounding problem, a ground current problem, and very much you avoid ground problems in process installation due to having all input outputs and power supplies isolated. On top of that, it is the optimal solution to power the sensor from the frequency converter, but if it's not possible, you should be fine with the isolated input and a separate power supply. So don't use the same power supply for the frequency converter and the sensor. Basically, there you have short circuit your isolation in the frequency converter. You have ruined the basic concept of the isolator. Question from Christopher. Again, is there any devices shown here that have SIL rating? And the question is, for now, there's no products with a SIL rating. We have prepared the 4225, and the paperwork is is ongoing. I don't have a target date for that yet, but it is planned. So if you require at least hardware assessment, then you should get in contact with our UK sales department and follow up on the 4225. They will be able to tell you when it hits the street, basically. We will also update our documentation, of course, but we can make sure that you get information when it is done. Are there further questions to today's presentation? We plan to run this very short seminar again in August and September, in case you have any colleagues or you know of anybody that could benefit from this kind of seminar.
I have one question.
Yes.
I'm sorry, I've jumped in and out your conversation and your presentation due to phone calls. But the question I had was on the 4000 series, what's the sort of starting price for it?
The 4225.
Yep.
I don't have it over my head, but I can look it up.
I can tell you in the US
Price
list
list.
price, yeah, the list price for the 4225A is $285.
Okay, so we're probably talking around 225, something like that, approximate. Okay.
There's a slight variation between the A, B, and C version, but it is in this range.
Okay.
If there's no further, yeah.
No, it's very,
ahead.
very good. It's an interesting presentation. It's very, very good. And let's say your products are really, really first class. So I'm sure it'll be
Thank you
something
very
I'll
much.
be using in the very, very near future. So thank you.
You're welcome. We hope to make it interesting, trying to make it a topic about what to measure and what to avoid, and a few tips and tricks and do's and don'ts, and less product gymnastics, so to speak. If you're more interested in the details of our products, you are always welcome. Come to contact our sales engineer. The invitation you had was sent by our sales engineer. Otherwise, our marketing at PR Electronics will reach me, and I will forward to your local contact if there is any questions you would like to answer about PR
Sorry,
Electronics products.
There is
Yes.
one more question from Hazel.
Is the difference between taco and speed pickup? Signal-wise, I would say no, basically. Very often the taco signal is of a north and south pole magnet that rotates at the end of a motor, or this dedicated unit we saw you can bolt on to the engine, or a signal that runs off an alternator on the motor. We see that on generators as well. So the signals are very much equal and analog in nature. And for that reason, as Michael told you, it's important to pay attention to signal levels and place your trigger levels correct to accommodate the varying voltage of the signal, varying with the speed of the measured signal, or speed of the measured rotation of the assembly. Okay, then I will say thank you for participating and close the meeting. I'll send out links for the recording after the meeting. Thank you very much for participating. Have a nice day.
Okay.
Thank you, everyone.
Bye-bye.
Bye.
Bye-bye.